Good day everyone, we are here to present our topic which is the concepts of system in engineering.
Good day everyone. In this lesson, we're gonna tackle and explore about the three concepts of system engineering, which are the systems theory, systems approach, and systems engineering. They are exemplified or showed in three dimensions of engineering, which are the science, design, and management. It is prominent in engineering, which aims to transform nature for serving the wants and needs of people. The engineering system concepts are compared to the notion of system as a seamless web in postmodern technology studies. As Friedrich Nietzsche remarked, being profound and seeming profound. Before that, profound means a person or something having or showing great knowledge or insight. It said that those who know that they are profound strive for clarity, means it strive for certainty, clearness, precision, and simplicity. Those who would like to seem profound to the crowd strive for obscurity. It means uncertainty or mystery. For the crowd believes that if it cannot see to the bottom of something, it must be profound. It, it is so timid and dislikes going into the water. I think in this quote, if you're obscure, you have the benefit of people's good nature when they assume they are too stupid to know what you're talking about, when instead it should be that your ideas are so weak that you have to hide them in wordy vernacular. And also, I think those who wish to seem profound do not want to fade into obscurity and anonymity. Rather, they want to be known as something they are not. So, rather than striving for obscurity, they strive to obfuscate. The profound strive to illuminate. Do you know what is a system? Maybe you've heard people talk about the solar system, or the school system, a family system, or a computer system. System is a small word for a really big idea. Systems are everywhere. A system is anything that makes up of different parts that work together that make things happen. It is an independent group of items, people, or processes working together toward a common purpose. Furthermore, then there are the more intangible political, social, and financial systems. They said the systems work when things go smoothly, and on the other hand, they say the system fails when the troubles strike. The people always blame or praise the system. Furthermore, a system is a buzzword in technology studies. Some technological systems example are everyday household, such as coffee makers, clocks, and even the doorbells. More complex examples are the cell phones, computer, and even the automobiles. On engineering, systems are central to engineering. Engineers are responsible for designing and building transportation, communication, and other systems that operate in the real world. Their system concepts are clear. Those are the system theories, systems approach, and systems engineering. In the book of Herbert Simon's Science of the Artificial, it gives the parable of the two watchmakers. Each designs a watch with 100 parts. The two watchmakers named Hora and Tempus, who made very fine watches. However, Hora prospered while Tempus became poorer and poorer. In Tempus' design, the 100 parts are so thoroughly interrelated that the watch totally falls apart if any one is removed. The watch is expensive because it must be assembled in one breath and cannot be repaired by replacing the parts. While the second watch by Hora has similar performances, but its parts are grouped into 10 modules which can be replaced if defective. Because it is simple to assemble and easy to modify, the second watchmaker, which is Hora, is able to offer his products at a lower prices and drive the first watchmaker, which is Tempus, out of the business. Watch design is similar to a seamless web, while Hora watch design is an engineering system. A seamless web is good, if perfect, but perfection is more often than not illusory. I could say that the seamless webs are prone to disasters because they can be unraveled by the tiniest of loose ends that may cause to the normal accidents, as Charles Perrow called it. To control such disastrous scenarios is a major reason for modularity. A modularity is the use of individually distinct functional units, as in like assembling an electronic or mechanical system. Furthermore, to limit the potential damages, engineers are careful to introduce seams and modular boundaries into their system. For example, is the electric power grid. Once the electricity is fed into the grid, it flows automatically according to physical laws and the conditions of the entire grid. An effect of a small mishap such as the lightning strike out a transformer can cascade through the grid, leading to power failures in large regions. For example, is the 1996 Northwest Power Blackout and the 2003 Northeast Blackout that each of them caused damages in excess of $1 billion. A system can operate seamlessly without being a seamless web. For example, is the internet, which is a patchwork of many networks, the landline telephone networks, wireless computer connections, satellite links, and more. The superiority of an engineering system lies not in seamless, but in its good seams or good interfaces between its parts. So I could say that system is really the central of engineering. So now, let us consider a familiar engineered system, an automobile. When you are driving it, it works as a unitary whole, but it is composed of many interrelated subsystems like the powertrain, transmission, ignition, steering, braking, lubricating, suspension, and more. Each of these subsystems is in turn made up of many parts. For instance, the clutch, stick shift, and gearbox for transmission. The gearbox in turn consists many components and so on down to the nuts and bolts. So even the car has a system, a subsystem, and even the components. So for now, we're gonna tackle what is the B model. We all know that the cars are designed by the engineers. So the B model, it is originally due to Forsberg and Moose. When engineers want to design a car, they do not start with the small components like the nuts and bolts. Of course, they start with the car as a whole. But of course, the car does not yet exist, but they start with the conception of the intended car because they want to design a car. More specifically, a set of functional requirements to how I build a car. Like what it's supposed to do, what performance are expected to the car, and many more. The first step is important and a difficult task, especially when the system is very complex. So after the design engineers have arrived at a satisfactory conception of the design of the car, they're gonna proceed to functional analysis. In this functional analysis, they will decompose the conceived car into the functional subsystems with proper interfaces. For example, a subsystem for power, a subsystem for transmission, and many more. And how those two, the subsystem for power and subsystem for transmission, are gonna work together, and after that they further analyze a subsystem into its interrelated components until they get to the specified last details. So after planning it, 8,000 of parts are manufactured. Then after that, they are gonna test and brought together and assembled it into larger and larger systems, and finally into a car that's ready for a test drive. So before we're gonna build a car, first gonna consider on the materials needed, the requirements, and we're gonna do a functional requirements, functional analysis, of course, to build a car. And back at the top of the B diagram or the B model, but this time we have a concrete system, a real car instead of a mere conception of it. On first, we're gonna think, or we're gonna just think the conception of it, and at the end of the B model, we're gonna have a concrete system or a real car. So the true functional decomposition, detailed design, and physical assembly, engineers know and specify the whole, its part, and their interrelation clearly and at all compositional scales. The advantage of the B model method is that it is very easy to understand and apply. The simplicity of this model also makes it easier to manage, but the disadvantage is that the model is not flexible to changes, and just in case there is a requirement change, which is very common in today's dynamic world, it becomes very expensive to make the change. So in short, the system's approach integrates analysis and synthesis. By the B model, it encompasses both the holistic and the modular views. We synthesize the knowledge about parts to understand the whole. We decompose the subsystem into subsystems and so on to the last details to make or build a car. So it also changes focus to view different levels so the mind is not overwhelmed by the complexity. Also, by the use of the B model, it simplifies the system by treating its parts as black boxes except their interfaces. It makes a complex system more tractable, and it controls damage and improves safety because, of course, we first tackled about the subsystems into subsystems and so on up to the last to make a car, so it controls damage and improves safety. Also because we analyze it into parts with proper interfaces, and we grasp the features into the whole system. The analysis and synthesis that we tackled on the last slide focus on internal structures, the internal structures of a car specifically. But of course, conversely, the ultimate goals of engineering systems, whether it is a car, bridges, or some structures, are to provide services to some external communities. Even when engineers concentrate on the internal structures of a system, they leave at least one crack open. The openings are represented by the functions, input, and output of the system. When we say input, it is the resources needed put into the system to produce a deliverable outcome. And when we say output, it is the deliverable of a system's processing of input. In conclusion, the objective of the system's engineering process is to create a final product, which is a system. Most engineers will tell you that the most difficult task of a complex engineering project is determining the requirements. The task is highly dependent on the cooperations of systems engineers and their clients. People are frequently unsure of what they want when it comes to complex systems involving novel technologies, or their expectations are high or unrealistic. So when clients are divided into groups, their desires frequently create conflict. So it is the responsibility of systems engineers to assist their clients in clarifying their objectives, like what exactly the clients want, or are they able to afford it, and if not, what other options do they have. The requirements are important because it is contain the behavior, attributes, and properties of the future system. Therefore, the main task of the requirements is to ensure that they are understood by all stakeholders or their client. In addition, requirements identify the product's business needs and purposes at a high level. They also clarify the features, functionality, behaviors, and performance that stakeholders expect.